All right, well, I guess I will start talking, and if people show up, then they can just come in and sit down and listen as well. Welcome, everyone, to this talk. It's PostgreSQL at 10 terabytes and beyond. And basically, what we'll be talking about today are problems that we ran into, as well as ways we went about solving them in a project that I worked on for Novozymes in Denmark. The database, when I started on the project, was only at 6 terabytes, but over the course of a year grew to about 12 terabytes. That's a huge amount of growth. That's a huge amount of data coming in. It's a huge amount of load on the database. So it's not just a question of volume at that point. It's also a question of velocity, and we'll even talk about some variety problems that showed up in our environment. I've been working with PostgreSQL in one form or another since about 1999. So my first Postgres version was 6.5. That was even before it was like safe to recover from a crash. And I've been working with it pretty consistently on a daily basis, roughly, since about 2007. So, been doing a lot of programming in the database, as well as programming against the database and database administration. So, wide variety of areas I've been involved in. So in this project, we were kind of out on the limits of what people were doing with PostgreSQL in a heavy production environment. And if you go to the Postgres website, you'll see something that'll say there are production databases over 4 terabytes, and you'll see something that'll say there are databases of over 32 terabytes. Well, we were running a production database, fairly production at any rate, dealing with a fairly large data set on a very high write load, with a fair bit of semi-structured data. This is not really a typical use case in Postgres. It's a very different world. I mean, I had been working in databases that were up to 200 gigabytes at the time, and here I'm sitting on a 6 terabyte database, and a query is slow. I'm like, well, how do I figure out which query is slow? We're having performance problems. How do I find out which query is slow, what we do about it, and so forth? And we're on a 48 core server, and a lot of the tools I'm used to working with just aren't very relevant in that world. So it was a huge learning experience for me, and what I'm hoping to do here is to provide some sort of takeaways that I think are applicable to more general database environments, rather than just sort of out on the frontier. This is a description of our environment. You see the database there in the middle, PostgreSQL. On one side, we have the grid cluster, and this was a scientific computing cluster. It had 1,000 computing nodes running 24 hours a day, 7 days a week, unless we put the system into maintenance mode or tune things down because something was causing a problem or something, which sometimes we would have to do. And then it would also display the information through a web server. The idea was we were building effectively something their researchers would use to determine what proteins they wanted to do physical research on. So this was basically, it's a research assistance tool. So making things very useful for their system is very important. But most of the database load, in fact, almost all the database load was coming off the scientific computing cluster. So, and even at 48 cores, I figured we were at roughly 25% load, pretty much all the time. Sometimes closer to 100%, but on average around 25% load. 7 days a week, 24 hours a day. That means if things continue to double, you only have 2 more years before you need more hardware or something else. So that's and that was a new server. I mean, they put the server in, and that's basically where we started. Now, this is no ordinary environment. You have a server with 3 terabytes of RAM. You have data coming in various different forms. Sometimes it comes in from one source. Sometimes it comes in from a published source. Sometimes, an internal pipeline. We have multiple different ways we have to process this so that we get everything into the same format at the end so people can use it. A lot of things we expect to work, like explain, analyze, don't do all the things we expect them to in these environments. You run a query, and on explain, analyze, it shows up 10 times faster than it does when you actually run the query, and you wonder why, even with the instrumentation overhead, is explain, analyze beating the actual query time. And you look at this under the hood and you start to realize, well, what's really going on is we have a bunch of fields we're pulling out that are toasted, that are stored off to the side. And as we're pulling these in, explain, analyze never gets to the point where it has to pull those out of extended storage. And so, little things like that end up throwing off your troubleshooting. And it becomes really important to have a pretty good sense of how things are working under the hood. So on the cluster, we would use a bunch of different software. I'm just mentioning a couple of these that are important for the perspective of our discussion today. The most important one of these is a program called BLAST, which does searches for similar regions in proteins or genomes or things like that. So BLAST we'll come back to in a few moments. It's a very, very important tool in the bioinformatics area. It allows you to search for one protein that's similar to another protein, or one gene that's similar to another gene, or something like that. We'd also be throwing in a lot of published documents, things from, say, EMBL or other science labs. We'd have a bunch of custom-written tools that would be running on the cluster, bunch of off-the-shelf components. I won't be getting into any of those other than BLAST. And then, of course, we'd have jobs that would update our full-text search, because we'd aggregate a lot of data and create full-text indexes off of them. And so that's basically what we were doing at the time. So now the database itself ends up being quite extraordinary. At the end of the first year, we were at 12 terabytes of data. Our largest index was 700 gigabytes in size. Our largest table was 6 terabytes in size, and that was the one storing the BLAST reports. We'll be talking about that in a little more detail later. We had tables with 250 million records for long-term storage, and we had tables with sometimes up to 500 million records that were basically being used as job queues. So this was so this is a different environment, and it has very different profiles when it comes to keeping performance up and keeping things running. So we're not going to talk about these problems today, except in passing. A couple reasons. Most of them were either solved before I got into the project, or else they were things that we just had to live with. I mean, you reboot the server and it takes 7 minutes to configure the memory and half an hour for the database server to come back up. There's not much you can do about that. Capacity planning just takes longer, and the fact is, anytime you introduce a change to your database logic, it just takes a long time to get things right and performing well. You make a change and things, get slow, and you have to figure out why and fix them. And that just becomes part of your routine. Usually the backup problems get solved when you're in the 1 or 2 terabytes range. Onto the major problems that we faced. The first one are work queues. So we pipeline all this data, we process it one stage to another, and we store the jobs in a table. Initially, we used this program or this Perl module called the Schwartz. It's on CPAN. It's a fairly simple module. It's designed to be robust and reliable at the expense of performance. And what we found very quickly was things weren't performing well. We'd go in, we'd look at PG stat activity, and we would see a lot of queries that were pretty clearly the Schwartz looking for jobs to run and taking 5, 10, 20 seconds to come up with a job. Obviously, that's going to kill your performance. And so we built a new solution around this. We solved that problem by moving a lot of logic into a stored procedure. We handled concurrency using advisory locks, and we got much, much better performance until the problems hit. Now, these problems are ones which illustrate the sorts of things that happen in this environment, and also how you can go about looking for and solving similar problems, even in smaller environments. So the first problem is Autovacuum can't keep up. Even the stored procedure would take a long time to find jobs to run. It would affect all queues, and you'd look at PG stat activity and you'd see Autovacuum running for 22 hours or something. I see some of you nodding. Evidently, maybe other people have run into problems with Autovacuum having trouble keeping up on a table in which you're deleting from very heavily. Now, one of the key things here to keep in mind is that we're deleting pretty clearly off the head of it, or we're deleting either off the head of one index or off a random point in another index. And what that would typically mean is that if we're trying to do a deletion off the head of an index, and Autovacuum can't keep up. In Postgres, all of our rows are stored in a heap table, right? And so the rows are unordered, but the index tells us where the rows are. The index does not tell us whether the row is active, right? So if we have a lot of these deletions going on and Autovacuum's not keeping up, we have to check each of these rows. Is this active? Is this active? Is this active? Is this active? No, it's not. 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 And in some cases, we were having to check millions of rows before finding ones that were active. So that's a very massive performance problem at that point. The second problem that we ran into, and I'm covering these two together before we talk about the solution because they were solved together, is that we would get really bad query plans on some queues. We'd expect it to use one index, and it would use a different index where it would have to check a whole bunch of rows before finding ones that it could use. And the reason for this is, if you go and you look at the PG stats tables, what you find is that you have these histograms of values, but they're only stored per column, right? So you can't say, oh, well, if this column is a certain value, then our statistical breakdowns change. So it would use the general case for all queues, and some of our queues we'd be delaying jobs for 4 or 5 hours, and the planner couldn't take that into account because it didn't know about it. So now let's talk about how we solved both of these problems together. Something that actually took us about 6 months. But what we did, the first thing we did was we partitioned the job table. Anybody here ever done any work with table partitioning in Postgres? Yes, not? Yes, okay. So what this means is instead of having one table for all our queues, now we had 80 tables. And we had to build some tooling around managing this because, 80 tables is a lot of tables to manage. And, you want to add more tables later. That meant that Autovacuum could now operate in parallel across each queue. One Autovacuum per queue instead of one Autovacuum across all the queues together. The second thing it meant was that the analysis grabs statistics per queue, not across the whole set of queues together. That means that our problem with bad query plans just went away. Of course, we had some other problems. The big one is we were selecting from the parent table, and that takes out a access share lock at plan time on every child table, which means doing database management is a real pain. You have to stop all jobs. You can't just stop some of them, right? And keep in mind, some of our jobs would run for 2 weeks. So you can't just you could, trying to turn them off and on, it poses some real problems. So we solved that by stopping using the ORM and just hitting the underlying partitions directly. The second thing we had was Autovacuum not clearing everything we thought it should clear, and that was because we had jobs running for 2 weeks and open transactions running for 2 weeks. So one thing there is Postgres does not actually have a full open transaction until you do a write. So by reviewing our code and figuring out where the database writes were coming from and deferring those on the jobs that were running for 2 weeks, we could essentially say, okay, well, we don't really have a full database transaction until the last couple of hours. And that would mean Autovacuum could suddenly clear a whole bunch more data that it couldn't clear before, and performance went way up. So that was a very, very clear win across those three pieces. So we solved those problems, and now we run into a very different problem. At this point, somebody pointed out, hey, look, we sometimes pull things out of the pipeline, and we want to make sure that we are not just sending lots of jobs out that are then going to have to be run again. So when we cancel something, let's make sure that we're logging and failing and doing a database rollback when a job disappears out from under us. Good thing. So we start seeing a lot more of these in the logs than we thought, and one of the people on the team says this doesn't sound right. And we spend a lot of time looking at this, and we eventually determine it's a race condition. It's a race condition in our job selection routine, or between our job selection routine and our job deletions. I spent several hours looking through logs, and I finally see that what's happening is a job runs, and then it immediately runs again. And on the second run, it fails, because it says, this was deleted out from under me. So the question is, why are we running this twice? So I'll explain the problem, and then I'll explain how we went about finding the problem and fixing it. So the gray area of this diagram represents the rows which are deleted but not collected yet by Autovacuum. The red ones represent the rows which are currently being worked on and are being locked using advisory locks. If you haven't worked with advisory locks on Postgres, they're very lightweight shared memory locking routines that you can test without waiting. So you can test them in a non-blocking mode. But they take effect immediately across database transactions, and they're tied to your database session. So if your database session goes away, your locks go away. It's nice in that regard. But they also take effect, and they also go away immediately across database transactions. So on the left-hand side, we have a process starting to scan and look for jobs. And on the right-hand side, we have another process that's working on some jobs that it has effectively said, we're working on these, they're locked, don't touch them, don't grab them to run them again. The problem is, if you have enough of a delay checking all those dead rows, what happens is that one on the right completes, and it releases its locks. Now, if anybody here has done work with Postgres and understands the snapshotting mechanism, what you know is that when you start your query, rows which have not been deleted yet are visible throughout the duration of your query, right? Because we want everything to be consistent within the query, right? But we're using advisory locks then to say, don't select these rows. So when the advisory locks go away, those rows are still visible in our snapshot, but they're not, but they have been deleted. And now we've gotten rid of the lock saying, don't touch these rows. So now we grab the job and we run it again, and it completes and says, what happened to me? And it dies. So the human side of problem solving in this case was very important because this is a very complicated problem, right? This is not something you just look at and go, oh, yes, I understand it. Because it involves a lot of things happening at different times. And, some people will say, well, maybe these jobs really were deleted intentionally. Maybe somebody deleted them out from under it. That could happen, right? So the first thing we did was we got like 3 people together, and we actually sat down and we talked about the problem. And we looked at different possible solutions. And we talked about what we thought was going on. And one of the people on the team, it wasn't even me, said he thought it was rows being visible in the snapshot after they had been deleted. And so we went through and looked at where we thought those were coming from, or where they might be coming from, and we were able to identify a couple of cases where it might happen. Then we talked about what to do about it. Once we kind of became convinced that this might in fact be the issue. This is something that's very hard to reproduce, so it's not like you can just go in and test it, right? And so if the snapshot's advanced, then the next thing to do is to double check the jobs when you get them back and say, are they in the next snapshot? Because we don't release the advisory locks until the snapshot's advanced, right? That was how we did it at first to try to avoid this problem in the first place. But so we did that. We rechecked. It's an extra database round trip, but we're not doing a full scan now looking for jobs. We know which jobs we've gotten. We're just checking to see if they're still active. And so that's a really, really fast query. The result, of course, is that we save ourselves on a bunch of other queries that would be run in those jobs that are that we don't need to run. So that turned out to be a fairly major win. So now we've talked about the job queuing issues. I'd like to talk about the denormalization solutions that we went through. Now, these had actually been implemented before I started working on the project, but they're something that comes up in Postgres a whole lot. And so they're worth talking about here in a little more detail. So I'd like to start off by talking a little bit about first normal form and the controversy about what first normal form is and what it really means. Now, COD defined first normal form as you divide your relations into fixed amounts of columns, and each column contains a atomic or a value that is not itself a set, and the relation is itself a set of these correspondences, which means every row is unique, and it also means you don't have sets within this. Now, we break this a lot in Postgres, right? People want to create a blogging system and they want it to perform well, so they throw arrays of tags on the ends of posts. And this performs fairly well, but it poses some specific problems, and we'll talk about the solutions to those. Now, I don't know if any of you are saying, but Chris Date says... Guess not. Chris Date is a very important database authority who basically says the atomic aspect of first normal form is meaningless. Are timestamps atomic? You know, we can decompose them into a date and a time, right? What about IP addresses if we store them as arrays of ints? I mean, does how we store something matter? Are phone numbers or ISBNs unique and atomic? Because, you know, I mean, a phone number may have a country code or a city code, or an ISBN has a publisher code on it. Now, Date's absolutely right. The problem here is that there's no ontological definition of atomic. You can't look at your data and say, this data is atomic, right? So atomicity has to mean something else. And what Claude was talking about, if you go and read his paper, his famous paper, I think it's called A Relational Model for Large Data banks, I think, is he was making a difference. He was making a distinction between an inferential system, a system that can draw inferences between pieces of data, and a non-inferential system like the network and graph databases that were prevalent before the relational databases came into the model, before they came into the picture. In fact, he mentions both network and both hierarchy and graph databases in that paper in a couple of decades ago. So I'm going to suggest a way of thinking about atomicity here. Sets of items are non-atomic because we have problems with foreign key constraints against individual members of those sets, right? So if we have a set of tags, we have no way of verifying that every tag in that array exists in another table, right? And that's the fundamental problem that you run into when you're talking about first normal form violations. The second thing is that you can't join, or you can't have a referential integrity enforcement between a sub-piece of data from a type and something in another table. So you can't say for every timestamp, we want to make sure that it exists in a year that's in this other table. Well, you can do it with custom triggers, I guess, but it's not really something that you can express very well in relational math. So in PostgreSQL, as I say, we break first normal form all the time. People do it, especially for performance reasons, when trying to make a lot of content stuff fast. So this is something which comes up all the time, and it has some very specific problems associated with it. The primary one is if you pull an array of tags, you have no idea which of those tags is still current or of value if you're tracking that in a different table of tags, for example. So here's a bit about our use case. This was our largest table at 6 terabytes. It's storing blast reports. So these are lists of proteins, or usually that are similar, and it's describing how similar they are. So it's coming up with a value of how similar they are. We generate all the rows associated with one protein at the same time. We insert them at the same time. We will delete them at the same time. And we always read them all together. Okay? So that's our use case. Without denormalization, our rows are scattered across heap tables. It takes we have to then do index scans to pull them. And sometimes we'll pull 100 and sometimes we'll pull 1,000 of these rows. Selects and deletes will take quite a bit longer. Inserts may take a little longer. And if we delete a protein sequence and we want to delete all the affected rows, that's going to be a much longer running operation. So, of course, if we denormalize, we can't say if we're deleting a protein reference, we're going to delete related rows, because that no longer means anything in a relational math perspective. Now, with denormalization, what we were able to do is basically, so you select the entire blast report at the same time. We had a new trimmed blast report in there also that would eliminate duplicates primarily, because you'd have possible duplicates in your database. These would then the whole blast report would fit in one toast page. But now we can't have referential integrity between the two sequences across that table, right? So we get a huge speed benefit at the expense of an integrity cost. Now, ordinarily, that's not a really good thing, right? Normally, integrity is king, and we sacrifice some speed to make sure that happens. But in this case, because of our access patterns and our database load, this was a real win. But what do we do about those orphaned records? So what we would do, and we would retrieve the rows, if we were retrieving them for display, is we'd unnest them. We would then join them against the other table and return the result. That seems like that's a really that seems like you're going to lose all of the benefits that you would get through denormalization if you do that, right? But one of the key things here is that the unnest function is planar opaque. So the planner doesn't have any idea how big your array is that you're sending it, right? So it plans for 100 rows, and it might get 1,000 out, or it might get fewer out, but it would choose a consistently good plan. And that made a big difference also. It would also mean that if we're pulling this for processing, we don't have to do that. We don't have to do that join. We can just filter things out because, we didn't find the sequence when we expected it. So the major trade-off, however, is space, and in particular, it's space in the main table. So now if you do a search on how many rows we have, that happens really fast, because that table has like 2 integer values for each row. Might have 150 million rows, but that's really fast. You're not scanning through that many data pages. So finally, the last case that I think is worth looking at, and this is also something which comes up in Postgres, is how we handled semi-structured data. Now, one of the key things here is that we were storing these structured text documents. And they could be XML, they could be JSON, they could be something else, right? But these were structured text documents, and they come in from a variety of sources, and we store their source and we store the text, and each source has its own format. But one of the important document types we were storing were patent documents. It's published in a very specific format called GenSigP. At some point, somebody says, we need to be able to sort these patents on the order of patent date. Had we grabbed the patent date out of these documents? No, we hadn't, right? And this is the table with 250 million records in it. So, what do we do? Obviously, we could write a worker and we could go through all these documents and pull out the patent dates, and we could do something like that. That's a possibility. But what we did instead was we extended SQL. And then, so what we did was we wrote a PL Perl function. It could be PL Python, it could be some other language. And basically it takes in the database row. It checks to see if it is a patent application. If it's not, it returns a null, because we don't want to do processing we don't have to do. And if it is a patent application, it returns the date. Simple, fast. And we mark it immutable, and we index the output. Yes, functional indexes. Then we build the index on, and now researchers can suddenly search on patent date. And they can order patent results on a given protein or things like that. And they can do that fast. And instead of taking us a long time to process the data, we had that up, within a week. So this is some very simple sample code. And basically, this is PL Perl, and of course it has the both the benefit of Perl of being very simple and easy to understand if you know Perl, and having the drawback of being totally opaque if you don't know Perl. And I don't think this is the specific code we used. This was something I wrote quickly as a illustration. One of the things about this is that PL Perl doesn't allow use statements, but you can use strict and use warnings. So in the event where you're using PL Perl, you can still use strict, and I highly recommend that. But you'll see you mark it as immutable. You can return it as a text string, and then use another function to, for example, cast it as a date. Obviously, something could go wrong here. If we ever got a malformed date in some file, we'd start getting database errors. So this is something worth possibly being a whole lot more defensive about when you're coding than we were doing, but it was something that really helped us out. And so here's an example of where functional indexes and this sort of thing really kind of saved our day. So then, just a brief bit about what I think the major takeaways are in this sort of environment. A lot of times, as I always say, as you go up one order of magnitude in database size, typically the sorts of problems you deal with change, right? So the specific problems that you look at 10 terabytes aren't the same problems you're looking at 1 terabyte. They're not the same problems you're looking at 1 terabyte as they are at 100 gigabytes, for example. Every time you go up one of these orders of magnitude, the problems change. But there are certain things which are sort of constant across that. The first is you want to get people together who are able to look under the hood of the database and understand what's going on, because databases provide a lot of abstraction from what's going on under the hood. And when you're faced with a strange problem, those abstractions are usually actually blocking your sight of the root cause of the problem, and hence what you need to do to fix it. The second thing is when you're looking at a new feature over a reasonably large data set, very oftentimes some of these advanced features like functional indexes can really come in handy in terms of saving your day, getting a feature out much quicker than you would have thought possible. right? And the final one I want to spend a little more time talking about is simulating, testing, and monitoring. We tend to think about writing tests. Writing tests that can run in the database. I mean, for the job queue stuff, we wrote a bunch of benchmarks. We wrote a bunch of tests. But some of these things are very, very difficult to test. For example, the race conditions. For some of these, one of the tools that we fell back on that I didn't really talk about in the previous slides was actually trying to come up with writing some simulations. When we wrote the second version of the job queue, one of the things I spent a couple of days doing was coming up with simulations of different algorithms of selecting jobs to see what would actually clear the job queues faster. And of course, those aren't like running in the database. Those were just quick Perl or Python programs that were trying to simulate the problems that I was foreseeing. And that actually helped narrow down the sorts of problems we expected to find, and helped us find solutions to them much faster. I know we don't often think about trying to simulate problems, but modeling and simulating problems is actually very, very helpful. And then the final thing is monitoring. One of the key things that we found was figuring out what to monitor on a database isn't always very clear, right? We ended up monitoring some things that we didn't expect to be important at first. Things like, what's the difference in value between our current maximum allocated transaction ID and our current minimum allocated transaction ID? That turned out to be very important in looking for and containing these Autovacuum problems. And that kind of gets back to this question of looking under the hood and always being willing to say, okay, yes, there's a whole bunch of abstractions, and yes, it's supposed to work this way, but it's not. And so if it's not working this way, let's figure out how it's working and how it's getting how we're getting into the situations where we've gotten ourselves into. And I guess the final thing I would say is that the human aspects of getting the people together in teams to solve problems that seem beyond the capability of one person to solve is something that I found to cut the time to resolution pretty dramatically. So I think those lessons are actually quite applicable even before you get to something on that scale. So that's the talk portion of this, and then I expect that in a few minutes we'll have pizza, and then we can kind of mix mingle and have just a general sort of discussion about these topics.